Before I get started, I just want to say a big thank you to the organizers, to the staff, to the sponsors, the other speakers, and you wonderful people for coming in here to share this with me. So let's give a round of applause for everyone. All right. So I am Dead Program. Some people call me Ron, a couple humans call me Dad, but in all of the important places, I am Dead Program. I mean, I'm not dead, not yet, but, and I am a technologist for hire. For hire. Get it? I was told to be very subtle when doing sales and marketing, so I run a consultancy called the Hybrid Group, where we create the software that makes your hardware work. And some of us contribute to a couple open source projects you may have heard of, like TinyGo, and also GoCV, which are the Go wrappers around the OpenCV. So this is about computer vision using WebAssembly. Computer vision using WebAssembly? I mean, why would you do that? Well, let's define the space a little bit. What we're talking about really is industrial computer systems. And for generally running on embedded Linux devices, or some type of edge computing device, or potentially as some type of cloud computing cluster. And applications are things like agriculture, transportation, energy, security, manufacturing, and retail kinds of applications. So not really home webcam stuff. A lot of computer vision applications have a very similar basic structure. It's some type of pipeline of processing vision data. But there's a lot of different parts to integrate. It's very hard to run on different kinds of machines, having the same application that you need to deploy the different hardware. And it's very hard to update. Oh, that sounds, and also there's some need for customization. Generally, it's not just like checkbox style parameters, but some type of logic involved. If a defect is detected, then reject that product, for example. So that's why we created wasmVision, which helps you get going with computer vision using WebAssembly. And basically capture video through a stream or a camera, process it somehow, and then save it, stream it, or do something because of what you discovered from it. So we have a wasmVision command line interface, the wasmVision engine, and then wasmVision processors. So the engine itself is written in Go, and it's based on OpenCV, which is really the gold standard as far as computer vision software. It's the oldest and probably most mature computer vision software. It runs on everything from Android phones, cloud computing clusters, small devices. FFmpeg, which is a whole other streaming system that many people have used for converting video. GStreamer, which is yet another complete toolkit for doing computer vision processing. GoCV, which is what's controlling all of this. And then WA0, which is our WebAssembly runtime. And all of this combined into a single statically linked binary, as long as you're running on Linux without a GPU. Some other rules may apply. So basically what we're talking about is this architecture. Oh, wait, sorry, that's something else. My mistake. That's a different unified architecture. I'm actually talking about this one. So as I was saying, we have the wasmVision engine, where we capture video. Then through the runtime, we pass those frames to the different processors, and then they can do different things with OpenCV, FFmpeg, or GStreamer. So you might notice from this diagram that the vast majority of the processing is actually being done in the host, in the engine, and not in the processor. So that's a pattern we're going to see a lot more of. So wasmVision processors can be written using Go, with TinyGo, can be written using Rust, or they can be written using the C programming language. And this is all because of wasmCV. So wasmCV is a set of WASM interfaces for computer vision that is defined using WIT. And we saw a couple of great talks yesterday about using WIT for generating client stuff. WIT is part of the WASM component model. However, wasmVision is not using the WASM component model at this time. It's just using WIT to generate client interface wrappers and documentation. So this is a very important point. You can use WIT without needing to use the component model. So what we're using on the host side is something called Wipes, which is a package created by my friend and colleague at Orsinium Labs, Graham, who actually has a really amazing handheld gaming system that runs WebAssembly. Check it out, Firefly Zero. So a quick briefer on how computer vision works. You have the mat, which is a matrix of data, some type. And then a RGB mat is generally how we would be representing color data. Usually it's BGR in the world of OpenCV, just an ordering thing. So now how WIT works, we have interfaces, and within those interfaces we have basic types we can define, like ints, floats, strings. We have records, which basically would be structs. It's a collection of data that's all together. And then we have resources, which are basically external references to things that exist on the host and that the client, the guest, is calling so that it does its work there. So let's take a look at the WIT file that's part of wasmCV. So we see here we've got our basic world of imports. We have the types. We have the mat. Let's take a look at the mat, since that's one that's particularly interesting. We see we have different kinds of mats based on the different bit depths and resolutions. We can create a mat. We can copy mats to other mats. We can see how big they are. We can merge them together, do different sorts of things. So that just sort of gives you an idea of what the API is like. So wasmCV docs are generated entirely from those WIT files, and here we can see this is the same mat functions as generated on the wasmcv.org website. So that just gives us documentation. And so let's take a look at a couple of the processors. The first one is the Go processor, and of course in Go we use package wasmCV to bring it in and able to use it. So to create that, we use WIT BindGen Go, which is a set of tools from the Bytecode Alliance that also some of the people who are maintainers of TinyGo collaborate and contribute to. Thank you, Fastly. And so the way, of course, we compile it is with TinyGo. We build. We target Wasm unknown. That way we have the most minimal, stripped down, bare bones, and efficient WebAssembly module. We say no debug and then blur. So let's take a quick look at the blur processor in Go. So we can see here it imports the wasmCV, CV, and mat, and basic types. And then it exports this process function. That's really the entry point for the module. It gets passed an image, and then it does something. In this case, we're going to call cv.blur, and we're going to blur it using a 25 by 25 kernel. So that's the size of the blurring mechanism. And then we're just going to return the blurred image. All right, so far so good. So let's actually see it work. So if we make blur, okay, and we're running it. And here I am, I'm blurry. Demo 1 complete. Gratuitous applause. All right, so far so good. All right, Rust. We can use Rust, very cool language. A lot of people like it. In Rust, of course, we use create wasmCV to bring it into our code. And the generation is done using WIT BindGen, which is another set of collection of tools from the Bytecode Alliance. To build it, we used cargo build. We target wasm32 unknown unknown in release mode, which will do as much as it can to get rid of any extraneous things. Let's take a quick look at the processor in Rust. We see it's very similar. No standard library. We have our crates that we bring in. We're using wasmCV. We have a process function, same idea. We get passed a mat, and we're going to return a mat. We take that mat, and we blur it using a kernel of 25 by 25. Have we seen this code a minute ago? And then we return it. Yeah, it's basically the same exact thing, just in Rust. So now let's see if that actually works. So if we make blur rs, so we run it. Oops, wrong pane. And we're still blurry, now this time in Rust. So far, so good. 2 demos down. You can applaud. And of course, C, the C programming language, venerable and respected. Who here has a copy of Kerning and Ritchie's book? Yeah, that's usually about the correct number, quite a few people. So of course, in C, we include wasmCV imports.h. And we're using WIT BindGen to generate the C bindings. And it's very simply compiled, just using a command line, something like this. You know, C is so easy, right? So just to be fair, All of these types of parameters are exactly the same ones that are being set by both TinyGo and Rust. It's just those are hidden. In C, these are explicit, so we actually know what's going on, for better or for worse. Let's take a look at the C code. It, of course, looks very similar to the code we've already seen. We import wasmCV. Our process function takes a mat image. It has to calculate the size of the kernel. It calls the blur function, and it takes the result of that and returns it. So again, very, very much the same code as we've seen. So now let's run the blur processor. Blur C. Keep going left when I want to go right. And we're still blurry. Same blur, same algorithm, same code, same WebAssembly, 3 different languages. Yes, it does work. You should be applauding for C, just because, like, when are you going to see C again? All right, so processors provide basic building blocks for computer vision. They can also be chained together so that the output of one is the input of another. And we can create our own processors, of course, since it's based on these published APIs and all open source languages and standards. A quick tour of some of the included processors that we have. So the Asyncify processor. The Asyncify processor is just kind of a fun one. What it does is it takes and processes, again, our image. It clears the screen on the terminal. It resizes the image. It converts it to ASCII. Right? We're gonna be matrixified, and then outputs that to the terminal, resizes that again to the size of the original image, and then writes that ASCII text onto it so we can stream as well as see on our terminal. All right. Let's see this work. Yes, it's me. Hello? Is anyone in there? Yeah, no, we want to stream this to the internet. I mean, isn't the Matrix on the internet? Like, are you there? Hello? Neo, come in. All right. Enough of that. So the wasmVision platform. So in addition to wasmCV, wasmVision itself has a platform. It adds some capabilities that processors need, like logging, configuration management, being able to make HTTP calls to external services, a data store, which is a key value store that's built in, where we can store data either associated with each image frame or with processors in general. And so I'm going to show you a little bit more complete of an application that I call creative captioning. So creative captioning is live caption generation with an artistic flair. And so here's how this works. Let's shrink this down. So we're going to capture the vision images, and then we're going to pass that to one of 3 different processors: the olama.wasm processor, the mosaic.wasm processor, and then the captions.wasm processor. So each of these is going to process an image in a different way, and then by using the capabilities that are built into the wasmVision engine, we're going to see the actual result. So let's take a look at the first one. So we also can configure wasmVision using TOML files. This way we can, instead of typing a really long command line, so we can see here our destination is port 8080. wasmVision has built-in MJPEG streaming as output. That's how we're seeing the output. This time we're going to CUDA enable equals true. So far everything we've seen has been entirely using CPU. We just introduced a new feature in the release earlier this morning, which allows us to have transparent GPU acceleration for processors. And then here's that pipeline again: Olama, then Mosaic, then the captions. And then our configuration is we're going to use the Nano Lava model. It's a large language model for vision, and it's a miniaturized version of the Lava model that some people may have already heard of. Sidebar, I'm going to have the MCP server turned off. We just also introduced an MCP server in the version this morning, so get your machine learning on. So let's take a quick look at the Olama processor. So the Olama processor, what processing that it does is, first it loads a configuration. That configuration is what URL we're going to use to call the external Llama server, or Olama server, what the default model is, and then what our template is. In this case, our prompt is going to be, describe what is in this picture in highly complimentary terms, using 6 words or less. Good challenge, right? So then the Mosaic processor does something different. What it does is it takes the image and then using something called fast neural style transfer, it's going to use a different machine learning model to take the vision images and to convert them into the style of a well-known artist whose name I can't mention because that seems unethical. But so we take and we convert that image into a blob, which is the necessary format for OpenCV and as a consequence wasmVision. We set that as the input to the Mosaic network. We process the data through the neural network, and then by taking the image data from that, we draw it back onto the screen. All right? You'll see more about that in a minute. And then the last one is the captions processor. So the Ollama processor takes the information that it finds and it saves it into the key value data store. The captions processor, what it does is it takes that image, it looks up the caption data from the data store, and then based on it, it draws it onto the screen for us. So we're going to have live captioning coming from our machine learning model. If the gods are good. All right, let's see if it's all still running. So far, so good. Well, let's see. If I Docker exec, actually, I already have it in the other window. Make sure that my lava model is running. It is. All right. Let's see it happen. Make captions. Wah. Oh. Uh-oh. Unreachable. Let's see. Something happened here. This is how you know it's real. Unreachable. Well, here, one thing we can maybe do is, let's see. This is what happens when you do a software release early in the morning. Development, wasmVision. Processors. Let's copy the Ollama Wasm to our normal processors directory. Let's see if that was it. Let's do the same also with, let's also copy the Mosaic and the captions. All right. Nope. I've done something wrong. What might that be? Pressure is on. This is how you know it's real, and also it's early days software. This is what you come to live demos for, right? Let's see. Let's see, make processors. Oh. No. There we go. Let's build all the processors up real fast. Just because. We have a lot of processors built in. All right. Copy Ollama, copy Mosaic, copy the captions. Oh, so sad. What's it not doing? We are running it. Here's an idea. Let's stop it. No, stop Ollama. Let's restart. Ollama. Let's load the model. And let's try again one last time before we move on to the next thing. Oh, that's so sad. Well, I'll show you that demo later. Um, I apologize for that. It ran right before I was on my way over here, but apparently not today. All right, well, that was going to be fun. Let's get to the last part, because we only have 9 minutes left. Video drone. So this is a flight control station using face tracking and a machine learning model, using my pet DJI Tello drone that some of you may have seen last year, and a DualShock 4 joystick. So let's take a quick look at the hardware. If we, let's see, make show video. Here's my camera. There's my DualShock controller, stolen from one of my children. This is my Tello drone that I'm pulling out of the case right now, along with a battery that I'm going to put into it. Let's boot it up. The Tello actually has 2 cameras. It has one camera on the front, which is an HD camera, and it has a second camera on the bottom, which is low resolution, generally used for flight stabilization. Now that we've seen what we're going to be playing with here. So for this, we're also going to bring in GoBot. GoBot is a physical computing framework that's been around for a while, that I'm the original author of. It has a different maintainer now. Supports many different pieces of hardware and software, running it from your embedded Linux, and that's what we're going to use for the control system. We're also going to use a UNet face detection model, which is a very efficient model from a research team in China. And just a quick briefing on how computer vision models work. Basically, we take the images. The input layer is just trying to locate where there are actual faces. Then another hidden layer says, oh, here are features of those faces. And then another hidden layer maybe says, here's the actual face itself. At that point, maybe we use a face recognizer network. This is just detecting the faces, not recognizing them. And here's the architecture of what we're going to see here. We've got our video drone program, which I'm controlling with the DualShock 4. It's going to send the signals through Wi-Fi. Oh, yeah, I should connect through Wi-Fi, shouldn't I? Let's do that. Connect to the drone. There it is. Actually, I should not connect to the drone if I want to show you the code. Connecting back to the conference Wi-Fi. Wait, which is the conference Wi-Fi? I'm not connected to that one. There was another one. A very long name. Is it the auditorium? Premature connection. I hate when I do that. What's the password for this conference? Wasm at BCN. Okay, yeah, sorry about that. I got excited. Okay, so that's going to communicate to the Tello. The Tello is going to send the video through a UDP stream, and then we're going to pump that through to wasmVision, which is going to then take that, send that to the face detection model, and then draw that onto our screen, doing this with the GPU acceleration. So let's take a quick look at that config toml. So our source is going to be the UDP connection. We're going to capture it using the FFmpeg and not just the webcam. We're going to CUDA enable, and then we're going to pump that through the face detect YN model. So let's take a quick look at the face detector code. Again, this is a TinyGo program written, compiled to WebAssembly. We're going to create the face detector. We do not need to know whether or not there's a GPU present. wasmVision will automatically accelerate it if there is a GPU, and will run in the CPU mode only if there isn't. And then the processing that we're going to do is we're going to take that mat, we're going to tell the detector what the size of the image is, and then we're going to try to detect the faces. When we take those faces, we're going to draw them onto the output mat and then display it. Drawing the faces is simply taking that list of faces, which is considered in another mat, Remember, everything in OpenCV is a mat. And for each one of those faces, we locate the face rectangle, features like the left and the right eye, and then we draw them on to that output. Interestingly, one other thing we do is we store the face data into the data store for that particular frame in case we want to do something downstream, like blur the faces, for example. Now, a quick look at the video drone code itself that we're going to run talking to the drone. We're going to start the joystick. We're going to start the drone. All we really have to do, luckily for us, is we take and we create a very simple proxy, two-line proxy that forwards the drone's video packets on so that wasmVision can read them in. We only do this because it turns out the Tello drone, which some of us helped reverse engineer a couple of years ago, you have to get rid of the first 2 bytes to turn it into normal video. All right, here we go. Now we connect to the drone. Is it still awake? Still awake. Turn off that video. All right. So first, we run the drone. Then we run the stream. Right? Right. Makes me wonder if there's something wrong with my, my GPU is wrong. I have a GPU in my laptop. Well, here's what we can do. No, wait, let's just try it one more time before we. Something's going wrong. Oh, do I have another video window open by accident? No, it doesn't look like it. Okay. Well, there's one thing we can do, which is turn off the GPU, since that is an experimental feature. I guess it would be under Demos, Video Drone, Config. I'm just guessing, but that's probably a pretty good possibility. Yeah, that looks like that's. We'll have to run in CPU mode, so it's going to be a lot slower. You'll see a lot more latency. All right. Let's move my camera out of the way, my other camera. Yeah, you can see it's a lot slower without the GPU. But we'll see it work anyway. Let's see if it can find any people. There's one now. There's humans. You only have to stay away from it for about 8 minutes, and then the battery will be dead. Don't think you people up there are safe. I was told I should only fly over the walkway. Let's see if I can get a shot of the stage. Oh, got to refresh the video. There it is. Yep, WebAssembly is getting pretty real, I would say. So this is just running with the CPU only. With the GPU, it's actually quite a lot faster. I'm going to have to look in to see what went wrong there during this morning's release. I guess we're going to have a 0.3.1 release this afternoon. All right, well, that's it for me. Come home, little drone. All right. So let's turn off the drone. It landed. Yes, that's good. It knew it landed. I'm going to fly the drone entirely with AI next demo. So I hope that was fun for all of you. Version 0.3 is available now, and version 0.3.1 about a few hours later. Check it out, wasmVision.com. You can find out more on the Featherverse at wasmVision.mastodon social and at Blue Sky, wasmVision.com. And thank you very much. If you want to see the Ollama demo, I will figure out what that is by lunchtime, and I can show it to you, because I swear that worked in my hotel room on the way over here. Any questions? Everyone's just stunned. Yeah, no, nothing yet? Nothing so far. All right. Well, see you at lunch. Thank you very much.